Here's a picture of a dry cell. Nothing you'd jump at to paste in your footlocker. But that cylinder can work magic like Aladdin's lamp. It lights lamps. It supplies power for radios. It even rings doorbells. Here's another picture, a storage battery. You wouldn't write home for this snapshot either. But take that battery, add a few more, and you've got the electrical energy that drives one of these deep-sea killers after a Jap convoy. Picture number 3, a gent named Alessandro Volta. Now, maybe you wouldn't grab your flashlight to look at him, Volta. You might not have lights. He's the scientist who found that chemical energy could be transformed into electrical energy. Volta worked out an experiment like this. You fill a container with a solution of dilute sulfuric acid. Put a piece of zinc in the acid, and then a piece of copper. It was almost 150 years ago that Volta did this. But what he found still holds good. The chemical gets to work on the two metals. Now, what happens? Well, attach a piece of wire to each of the metals. Connect a bulb, and you'll get an electric current. There's your proof, electricity. Because Volta worked this out, any device that generates electricity from chemical action is now called a Voltaic cell. In any Voltaic cell, the plates are called the electrodes, and the chemical solution is called the electrolyte. Let's see what happens first with only the zinc plate taking a bath in the acid. There's a chemical reaction. The zinc starts to replace the hydrogen in the solution. Those bubbles are the hydrogen that's being replaced. After a while, you can see that the acid is making a good meal of the zinc. Something else is happening at the same time. As the zinc is eaten up, some of its electrons take off and help form the hydrogen bubbles. Now let's see what happens when the copper is put in the acid and both plates are connected in a circuit. This time the electrons detour through the wire and lamp to the copper electrode and then travel to the bubbles. This electronic flow is what gives you an electric current. And so, from the chemical energy that naturally exists in the materials that make up a Voltaic cell, you get electrical energy. You can rig up a Voltaic cell with any acid, alkali or salt, and any two unlike conductors. But your voltage depends on the combination of materials. For instance, this copper and zinc in dilute sulfuric acid gives you about 0.8 of a volt. On the other hand, with carbon, and make a carbon zinc cell, and you'll get more voltage. There, the carbon zinc cell gives you about 1.5 volts. Now, while the combination of materials does affect your voltage, the size of those materials does not. Look, here are two cells. Both have the same combination, carbon and zinc in dilute sulfuric acid. Obviously, one is much smaller than the other. But the small one gives you as much as the other, 1.5 volts. You can have a cell as big as a pup tent, but as long as it's made of these same materials, you'll get the same voltage. That doesn't mean you can't increase voltage. You can, by connecting the electrodes of two or more cells in series, which means just what it says, one after another. First, connect the zinc electrode of the large cell to the carbon electrode of the small one. Now, all you do is connect the other two electrodes to the voltmeter, and you can read the combined voltage. You had 1.5 volts before. Now you have 3. There's 1.5 volts for one cell and 3 volts for the 2 cells in series. While the size of a cell doesn't make a bit of difference in the amount of voltage, it makes all the difference in the world in the amount of current. The bigger the electrodes, the more amperes you can get, because more surface is exposed to the chemicals. Let's measure the current. The big cell gives you 0.2 of an ampere. The small cell gives you only 1/10 of an ampere. So that's the story. Current depends on size. Voltage depends on combination. Now let's see what a cell does when the current's being used. First, we'll connect a voltmeter. Now connect a resistor that will draw current. Watch the voltage drop twice. There. The first drop is swift. The second is gradual. You get the first quick drop because the cell itself puts up resistance to the current. There are several things that cause this resistance. For instance, the liquid and what it's made of. Then there are the electrodes, what they're made of. How big they are. How far apart they are. The age of the cell counts and how much it's been used. All this resistance inside the cell is called internal resistance. And that's what caused the big drop in voltage when you draw current. The second slow drop is caused by hydrogen bubbles forming at the copper electrode. These bubbles insulate the copper. The more bubbles that cover the surface, the more resistance to the current. So the voltage drops lower and lower. This is called polarization. If you remove that insulation by brushing away the bubbles, the voltage goes up again. The principles of the voltaic cell are used in the storage battery. Everything that goes on inside a voltaic cell goes on inside a storage battery because it's simply a voltaic cell with a lot of plates connected together. The positive plates form one electrode and the negative plates form the other. To keep from touching, they're separated by an insulating material. They're built like this to save space, to cut down internal resistance, and to step up the current. These batteries have hard rubber containers. This one has 3 cells, hooked together by burned-on lead connectors. This makes a tough, compact battery that can take quite a beating in the field. However, a good thing about a storage battery is that when the power is used up, you don't have to throw it on the junk pile. You can recharge it. An ordinary lead-acid battery shows just how this works. The positive electrode, the dark one, is made of lead peroxide. The negative, of spongy lead. And the electrolyte, of dilute sulfuric acid. Now, as the cell discharges, the surfaces of both electrodes are gradually turned into lead sulfate, and the acid is gradually turned into water. Just the same, although the chemicals change form, none of them escape from the cell. Now shoot a current through the cell in the reverse direction, and you reverse the procedure. The cell is changed back to its original combination: lead peroxide, spongy lead, and sulfuric acid. Just because you can recharge a lead-acid cell, don't wait until the cell is exhausted. Stall a little too long, and the battery will become sulfated. The surfaces of the electrodes will become completely covered with lead sulfate, which is a non-conductor. And that means you'll never be able to recharge that battery. A battery can become sulfated even when it's just sitting on the shelf. The chemicals inside never stop working. For permanent use, such as fixed radio stations, cells are housed in glass containers, just so you can watch them closely for sulfation. To prevent sulfation, you've got to check your batteries regularly. How? Well, one way is with a hydrometer. A hydrometer tests the specific gravity of the electrolyte, which is a fancy way of saying it finds out just how much water has formed in the cell. Put the tip in one of the cells, squeeze the bulb, and keep your eye on the scale. 1275. Good. The standard for most batteries is 1270. Anything under means you've got to watch the battery like a hawk. And if it drops below 1170, recharge at once. There's another way of checking a battery by using a voltmeter. When you test with a voltmeter, make sure the battery is delivering its rated current. Connect a resistor to the battery which will pull the rated amount of current. You should get at least 2 volts for each cell. That is, 2 volts for each pair of electrodes. The reason the battery must be working when you test it is that even a half-shot cell will read 2 volts when no current is being pulled. Another type of voltaic cell is the primary or dry cell. This can't be recharged. If one of these goes bad, get a new one. A dry cell has a cardboard case for insulation and protection, but inside that is the real container for the cell. This is made of zinc and is the negative electrode. The positive electrode is a stick of carbon. The filler, a mixture of finely crushed coke and manganese dioxide, is a depolarizer. It absorbs the hydrogen bubbles which would otherwise hang onto the positive electrode and insulate it. The manganese dioxide is kept away from the zinc by a layer of blotting paper. The whole works are soaked with a solution of sal ammoniac, and that's your electrolyte. So you see, the cell really isn't dry, it's more like a paste. In fact, if actually it dried out, it would be useless. To guard against that, the whole works is made airtight. Dry cells come in different sizes for different purposes. For A battery use in a radio set like this, you use these BA23 cells. One of these gives you about 1.5 volts. The flashlights these soldiers are using obviously call for a smaller cell. So when you get a dry cell, make sure to choose the size that'll fit your equipment and give you the amount of voltage you need. These soldiers, by the way, are going to tear down their equipment because they're breaking up camp for a month or longer. When you're in that spot, be sure that you remove any batteries you've been using. Why? Because even if a cell is not being used, the zinc container will corrode by natural chemical action. That gives the electrolyte a chance to leak out and a chance to damage your equipment pretty seriously. The reason a cell will go to pot, even if it's not in use, is that there are impurities in the materials. In any case, you can't expect a dry cell to last more than 12 to 18 months, even though you keep it on a shelf. You have to use a voltmeter to check a dry cell, and when you do, make sure that the cell is delivering rated current, just as with the storage battery. Turn on the current. This cell registers 1 volt. If the cell is good, its voltage shouldn't be less than 1.4 volts. This cell is no good. You've got to replace it with a new one. This one is okay. Test all the extra cells you've got on hand, and test every cell before you take it into the field. Now let's go over the whole thing. Here's the basic principle of the voltaic cell. Two different conductors in an electrolyte give you electric current. The storage battery is a practical voltaic cell. It should be tested frequently with a hydrometer or with a voltmeter to see if it needs charging. Use the storage battery when you need comparatively large amounts of voltage and amperage, as in trucks and radio stations. Check dry cells with a voltmeter, but be sure that the current is on when you do it. Use the dry cell when you need small amounts, as in flashlights and some radios. Replace bad ones immediately to ensure efficiency. And don't leave batteries in while the sets are stored away. Keep those batteries in condition, and you'll keep your equipment working.